Pick up your colored pen. Number 1, what is the value of x? And we will go to student number 14, 17, and 2. Student number 14, what'd you get? 30, okay. Number 17, what'd you get?
X equals 30.
Do you agree? Student number 2, what'd you get?
X equals 30.
You all think that x equals 30, and it does. Now, number 2 was a slightly different question. Describe 2 different paths of logic to find the measure of angle ACB. So, for example, you would say, kind of like an informal proof, you would say, well, by the external angle theorem, I was able to find angle C, or BC, and there was no letter over here, so we can make one up, BCD. And then, since I know the linear pair postulate, and so we say things like that. So let's see what you came up with. I'm going to call on you. You're going to give me one path of logic. One path of logic. So we'll start with student number 5. Student number 5, what was your path of logic?
Linear pair postulate of 7x minus 50.
Okay.
Plug in the x back in, and you gotta find the linear pair of 20.
Okay. So we take the x that we found, plug it in here, and then using a linear pair postulate, that tells us what?
That the whole equation equals 180.
Okay, so that the pair of angles will be supplementary and they will equal 180. That's one path of logic. Number 15, what'd you come up with? Exterior angle theorem tells us what?
Tells you what C plus C.
Mm-hmm.
I did 2x plus 10 plus 3x equals 7x minus 50.
And that gets you what?
That got me. Wait, answer? I lost it.
Okay, you're not lost. It got you what? You're the one who said it.
That x equals 30.
Good, x equals 30, but I'm asking you to give me this angle.
Oh.
I asked for 2 different paths of logic to get that angle. You just answered question number 1. And that was a great explanation for question number 1. But I want angle ACB. We'll come back to you. Think about it now. Student number 20, what'd you come up with?
I didn't finish, but I was thinking
Vertical angles.
yeah, if you block out the A and B, if you put the
So if I block out A and B, so if I do something over here like this, okay, that's cool, I like that, and then what?
I guess you would extend the slope, the transversal.
Okay, nice. Extend this line here, like through here. Okay, so if we could do that, extend that, see if I can do that. Okay, so this is drawing an auxiliary line, which we learned about a few days ago. Okay, and then what?
So because it has to be from 360 to 7x minus 50 would go on the
Well, we already know what this angle is because we found 30, so we could have already plugged that in and figured out that angle. So could someone tell us what this angle is right here? What's its value? Brandon, what's its value? It's 160. So we already know that this is 160. So go ahead, continue. Okay, so this angle is congruent. Oops, excuse me. This angle is congruent to this one because they are beautiful. So that's 160. This is going to be 160. Beautiful. But I'm still trying to find this angle over here. Yeah?
Because you say 360 minus 220 equals
You said 360 minus what? Minus 320. Okay, where'd you get the 320 from?
You add the
Okay, so you added the 160, got 320. So now how much do we have left over? 40, beautiful. And then you did what? Divided by 2. Why are you allowed to divide it by 2? Like, why could you divide it by 2? Why not 3, or why not 8, or why divide by 2? And the two angles we know are going to be, they're going to be congruent to each other, and if they're congruent to each other, then we have to take the total measure and divide it by 2. Okay? I'm going to assume that the little side discussions are trying to figure out your own path of logic. That would be great. If that's not the case, then you're just being rude. So let's try to make sure we're doing the right thing. Okay, so that was totally roundabout, kind of interesting way of approaching it. I love the creativity. There's 1,000 different ways to do it. That's one. Good. Michaela, what'd you come up with?
Since it was a triangle, you know the inside has to equal 180.
Yeah.
You know what I'm saying?
Yeah.
So you could just plug the x equals 30 into 3x, 2x plus 10, and you get 70 plus 90 equals 160.
Beautiful.
180 minus 160 equals 20, and that gives you
Beautiful. That was a fantastic explanation, and it's exactly what we're talking about. Because because of the triangle sum theorem, that the 3 angles inside the triangle have to add up to 180, and because we already found the 30, we know this angle and we know this one, we can simply find the third angle. Beautiful explanation. That's what I'm talking about when I say path of logic. So we didn't have to write a proof, we thought through the logic. Beautifully done. Any other comments, questions? Any other paths of logic that you'd like to share? Tristan?
You could substitute put 30 for x on C, then that would have got 160.
Mm-hmm.
And by the linear pair postulate, you could have subtracted 160 by, wait.
That's right. And that's what we talked about, is that this is 160, and these two angles are a linear pair, and a linear pair is, and what word describes that? The supplementary, and so you subtract it and you get that angle. So no matter what, no matter which way we do it, we get 20 degrees. Very nicely done. Any other questions, comments, or concerns? Last time we were together, we took a small little side trip. It wasn't really a side trip, but it seemed like it was, to talk about transformations and how it applies to congruence. Prior to that, we had been discussing triangles almost exclusively, and now we're going to go right back to triangles. Today's lesson is about proving triangles congruent using one method in particular. It's called the side-side-side congruence postulate. So, first, our objectives. We would like to, by the end of today, be able to apply SSS, or side-side-side, to construct triangles and to solve problems, and to also prove triangles congruent. New vocabulary, you're going to hear the phrase triangle rigidity. Okay, so, first off, in 4.2, not the last lesson, but in 4.2, we talked about triangles being congruent by showing all 6 pairs of corresponding parts. And I talked about, when we did a proof, that we had to gather 6 pieces of evidence to prove the 2 triangles were congruent. 6 pieces of evidence. That was a lot of evidence to gather. But you're going to learn something today. That because of triangle rigidity, we end up having actually a shortcut. And from now on, it's like graduating to the next level. You will never have to prove all 6 pieces of evidence, because 3 pieces of evidence will prove to be enough. If we have the side lengths of the triangle, and they're the same as another triangle, then they can only have one possible shape. And that means that the other one would have to have the exact same shape. Okay? Again, if you have 3 sides of a triangle given to you, it can only form one particular triangle. Okay, so let's talk about the postulate. It's on your cheat sheet. It's quite simple. If you have 3 sides of one triangle congruent to 3 sides of another triangle, then the triangles are congruent. Prior to today, we had to gather the 6 pieces of evidence, which included showing that, and that. So we needed the 6 pieces of evidence. We no longer need those pieces of evidence. We can just show by side, that the triangles are congruent. Does anyone have any questions about that simple idea? So let's go ahead and start using it. Example 1. We're going to write a proof. So, I've been talking about the idea of the smoking gun for a couple of weeks. And I'm getting a little lost in which group I spoke to about which idea, but I'll reiterate it again anyway. The smoking gun is the easiest way to prove something. If you can find the smoking gun, Davis, then you've proven your case. But what if there is no smoking gun? Well, then you have to gather evidence. And when we were in 4.2, we had to gather 6 pieces of evidence, and there was no smoking gun. All 6 pieces of evidence had to be there for us to then prove our case. Now we need 3 pieces of evidence, because look at what we're being asked to prove. We are being asked to prove that triangle KLM is congruent to NLM. And it's hard to come up with that smoking gun statement, that golden statement that comes right before the proof statement. It's hard to come up with one thing. But because we know side, if we can show that all 3 sides are congruent to the 3 sides in the other triangle, then we've proven our case. So let's go ahead and gather the evidence. Some of the evidence is at the crime scene. Some of the evidence is sitting there waiting for us to find. What do I mean by the crime scene in this case? Where's the crime scene in this page? Jada? The given. That's the crime scene. Right here is the evidence just given to us right off the bat. So how many pieces of evidence do we now need? 3. How many are given to us at the crime scene? 2. So we just have to be detectives to find that 3rd piece of evidence. Let's start out by stating the crime scene evidence, or the obvious, the ones given to us. Okay? Segment KL is congruent to NL. That's crime scene evidence that's given to us. We can wrap both pieces of evidence into the same statement if we want to be super lazy. That's not really being lazy, that's just being efficient. So then we're also given that segment KM is congruent to NM. It was also given. So we just have to find that 3rd piece of evidence. So what's the 3rd piece of evidence that we need? Fung? Yeah, the 3rd side of the triangle is actually a shared side right here. So we have to prove that this is equal to itself. And so she already made the statement, segment LM is congruent, excuse me, that wasn't very good, to LM, but what is the support for that? Why are we allowed to say that? Dalton? The reflexive property of congruence. Now we have our three pieces of evidence. Now we can say our proof statement. Triangle KLM is congruent to triangle NLM because of what? What proves that statement? Sebastian? Yeah, and you can put SSS congruence postulates. Or you can put CONG postulate, whatever you want. Side, 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 congruence postulate. Does anyone have any questions about how we completed this proof, or about this analogy that I'm now using between crime scene investigation and law and doing a geometric proof? Does anyone have any questions or comments about that? Well, give it a few minutes, and if you still have the same question by the end, you ask again, okay? All right. So, I'm asking a slightly different question that I want you to explore. Use SSS. So I'm telling you right off the bat, you're going to use side, side, side to explain why triangle ABC is congruent to triangle DBC. So I'm not asking for a formal proof, but I still want a path of logic. I want you to explain why it's true. Okay? So it's more informal. It's not going to be listed perfectly in a T-table. It's informal. But you need to explain. Okay? Any questions about that? Take about 2 minutes. Of course, if you have any questions, please let me know. Well, triangle rigidity is just an idea. So what do you want to say about it? Make a statement. I didn't do a very good job of explaining the idea is this. Okay? If I give you three lines, there's only one triangle. But if you give me 4 lines, everything quadrilaterals. All right, so how could you use side, side, side to say that those two triangles are congruent? How could you do it? Chris?
Okay, so first of all, line segment AB and line segment DB are congruent to each other.
Good, and I love how you paid attention to the order of the letters. That was very good. Go ahead, keep going.
Line segment AC is congruent to line segment DC. Both of those are given. And line segment BC is congruent with some reflexive property from
Very good.
And since all three sides of the triangle ABC are congruent to their corresponding sides in the triangle ABC, two triangles are congruent to the
You can't get an explanation much better than what he said. Cannot get much better. In fact, I would probably rewrite mine to match his a little bit better. So it's given that segment AC is congruent to DC, and it's given that segment AB is congruent to DB by the reflexive property. And notice that he said that by the reflexive property, segment BC is congruent to itself. Therefore, by side, 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 triangle ABC must be congruent to triangle DBC. So did you have to have it worded like this? No. Did you need to be able to lay out these elements in an explanation somehow? Absolutely. Done. Yes. Yeah, and I am finding it actually difficult myself. That I'm noticing that I make mistakes with letters because I tend to go in alphabetical order just naturally in my head. So when Chris said segment AB, I wanted to say BD. But he was correct. It's AB is congruent to DB. The order matters. Has to be in the right order because the letters match each other based on the statements that were given or based on the picture. So thank you for pointing that out. Absolutely. So I know that if I'm struggling with it, there's probably someone in the room struggling with it, although you guys are much smarter than me, so maybe you're not. Are there any comments, questions about checkpoint number 1? Okay. So, now let's look at something related. You do not have to copy everything, but you need to read, and we're going to be working on a little activity together. Triangle JKL has these 3 vertices. Triangle RST has these 3. Graph the triangles and then show somehow that they are congruent. So let's see what coordinates we have. Looks like we have coordinates that go all the way up to 10. So you're going to need a grid on your paper that goes at least 10. So go ahead and get a grid set up. I'm going to set up a grid as well on my paper.
Yeah.
And let's go ahead and just get the elements down. So J is at -3, -2, 2, 3. So there's J. K is 0, -2, so that's right there. And L is -3, -8. So I'm going to have to go down a bit. -3, -1, 2, 3, 4, 5, 6, 7, 8. And that is going to form a triangle. Any questions about that? So this was J, that was Okay, now I'm getting confused. K and L. Any questions about how we put that down? That's pretty basic. And then RST. R is 10, comma 0, 1, 2, 10, negative 3, and then 4, comma 0, 1, 2, 3, 4. And this was RST. So R, S, and then T. So how can we prove, well, I'm sorry, let me give you a moment. Just give me a thumbs up if you've got the picture down. Okay, a lot of us. Good. So how can we prove that they're congruent? Only using anything we've learned today or prior. How can we prove that they're congruent? We'll start with Brian and Jacob. Okay. What did you say? You said find the distance of all three sides?
Yes.
And then what was the second thing you said?
No. And see if the corresponding side
Oh, okay, good. So we can find the distances of all three sides. Jada, what were you going to say? Okay, so we could use the patty paper, trace it, but we're trying to do it mathematically now, so that's a different type of approach to prove different types of points. But for right now, we're trying to not use that system. We don't want to use a protractor or a tool. Mathematically, we want to show it. Okay? So, could someone give us one of the distances? Tell me a segment and give me a distance. Brandon, give me a segment and tell me a distance. RS is 3. How'd you figure that out? Oh yeah, you count. 1, 2, 3. Oh, look at that. Okay, so that's 3. 3. Okay. So that's a distance of 3 right there. So give me another segment and give me a distance. I'm going to start calling on random people, so because this is not challenging part. Tristan?
TR is 6.
TR is 6. How do you know? Oh yeah, you count. So that's 6. Okay, so we got that distance right there. Good. Give me another one. Give me another distance. Ania? JK is 3. Are you sure?
Yes.
Yes. We're sure. Give me another distance. Davis?
JL is 6.
JL is 6. Are you certain?
Yes.
Okay, so we can count that. So we can see that we've got a 3 and a 3 and a 6 and a 6. But based on what we know so far, what has to be true to say that they're congruent? What has to be true to say that the two triangles are congruent? Kayla? All three sides have to be congruent. So how are we going to get the final distance? How are we going to get KL, Ann?
Well, it's a question.
Go ahead.
Can't you just find the slope of each hypotenuse and compare it?
Well, that's a good question, and I had the same thought myself. The problem is that if the line continues on, like so. Do these two lines have the same slope? Do they have the same distance? Wait, do these two lines have the same slope? Yes. Do they have the same distance? No. So I agree with you that it seems like there should be something we could do, but I'm not 100% sure how to approach it. So let's table that for a couple of minutes, see if we can figure something out, and let's try a different approach. What's another approach we could take? Chris and then Sebastian.
Actually, don't we already know that the two triangles are congruent because two of their sides are congruent, so the third side wouldn't like the third sides have to be wouldn't the sides that we have congruent measure have to be congruent since the other two sides are congruent?
No, because what if I took this side? I don't know if the computer's going to let me do it. What if I took that side and went like that? And it was the same distance, so I didn't affect its distance. And then I changed this so that it closed. Well, it's not letting me do it, but it let me connect it over to here. So, unfortunately, can't just assume that the third side is congruent. Sebastian, you were next. The distance formula of the 2 point. Give me an example. What 2 points? TS, and then find the distance between them, and that gives us the third distance. Okay, that makes sense to me. So let's go ahead and do that. That's pretty simple. So TS will be the square root of the difference of the x's squared plus the differences of the y's squared. So let me write it down because I need to see it. So that's 4, 0. And this is 10, -3. Is that right? Bless you. So we got 10 minus 4, so that's 6 squared, and then we've got -3 minus 0, that's -3 squared. Yeah. That's I'm not sure. That could be a coincidence, I'm not sure. Keep paying attention on another one, see if it happens again. Okay, so we got 6 squared is 36, and a -3 squared is 9, so we've got 36 and 9. So we got the square root of 45, and we don't need to actually simplify it because we just need to know, is KL going to be the same distance? So we now know this distance right here is radical 45. So let's try over here, KL. K is 0, -2, and L is -3, what was it, -3, -8. So let's see what we get for KL. Differences of the x's, differences of the y's. Differences of the x's, 0 minus -3 is 3, and -2 minus -8 is 6. And I can already tell it's going to be the exact same thing. This is going to be radical 45. And so we get the exact same distance for the third side. So now that all three sides are congruent to three sides of the other triangle, now we can say by side, side, side that the two triangles are congruent. So I took a little bit longer on this. This could have taken 3 minutes, but the idea was to think about some different approaches. I think Anne is onto something, and I think Chris is onto something. But there's other elements that you have to think about, okay? And you are definitely onto something, but there's another piece of it that you got to figure out. Chris, you're kind of onto something. Think of some other things on the cheat sheet that we're going to discover soon. I did this, I turned this, and that should have been a little bit of a clue about why, when can you say the third sides will be congruent because these two sides are congruent? There's something that has to be true also. Okay? Don't say it now, but you're going to discover it soon. Catalina, yes.
I was gonna say because you can see that segment TR and SR are perpendicular, so they have the opposite reciprocal slope.
Okay?
So I was gonna say that, and because it looks like to me that that's similar to the third angles theorem. Because you know how the angles say if two of the angles are the same, then the other one is going to be coming to the other one.
Interesting. So you're saying that there's a theorem called the third angles theorem that says if two angles are the same, then the third angles must also be the same. And you're saying, well, does that work with sides? Is there something called the third side theorem? It's a very interesting point. Let's see what happens in the next few days. Okay? And I love how you described how you knew these were perpendicular. That was fantastic. What you pointed out that they had opposite reciprocal slopes, which was easy to find out because this is zero slope and this is undefined. Easy to figure out. And that also is true over here. But then how does that help us? Okay? So, Dalton, and then I got to move on.
I thought it's so common because the side and
Mm-hmm.
side.
Right, but we didn't learn that yet, so now you're just cheating. I said, that's why I specifically said things that we learned today and backwards. Okay? All right. So now, example 3, I don't want you to write it. I just want you to write example 3, but I don't want you to draw anything. I don't want you to write anything. But look at the question. Explain why the bench with the diagonal support is stable, while the one without the support can collapse. So, I didn't do a very good job of explaining triangle rigidity. I'm going to go a little bit deeper now. So first of all, I want to show you something. So this is a website, and there are quite a few different ones. It's called Maths in the City. And I want you to look at some of the pictures, and keep in mind that my projector is still not showing the colors properly, but I want you to look at some of the pictures that are here. And unfortunately, it is not as good as it could be because you're supposed to see some red outlines, but I want you to look right here, and right here. What shapes are being, and look over here, what shapes are being used to support the hammock? Triangles. And now look at this one, you can see a little bit better. This, let me shrink this down a little bit. So this was the full picture. So this is on a playground, and so this triangle support is holding this up, and it's forming these triangles. And now look at this activity that this person, this swing that this person is going to climb onto. Look at the way the chains are connected to the seated portion of the swing. And then this type of swing is a little bit of a stretch, but you can see that it forms a triangle when, can you see it? Yeah. A triangle when you connect. Here's where it becomes incredibly important. This is a famous bridge in England. And I don't know if you can see, let me make it a little bit bigger. But the entire thing is made out of triangles. You can see it a little bit better over on this side and maybe on the sides over here. The whole bridge is triangular. And so this tree is being held up by two 2x4s that were connected right here at this point, but they form a triangle. Why are triangles being used so frequently to support objects? Because of the idea of triangle rigidity. And so here's an experiment that you can do, and I'll post this website on, connect this website to mine. If you take a regular piece of paper and fold it so that it forms a series of triangles, look what it can do. That single thin piece of paper, folded into triangles, can support the weight of a couple of books, just based on the fact that they're made out of triangles. So, could you see that? It's a little hard to see, but this is made out of triangles. And so the triangles form the support. And so this has to do with triangle rigidity. And the point is this, that when you take 3 lines, there's only one possible triangle to make out of it. But if you take 4 lines, there are several different quadrilaterals you can make. So go back to this. This triangle right here can only be formed one way. It's rigid. It can't all of a sudden morph into another triangle, but look at this. Here, this is the support system for this. But what would happen if this side tilted this way and this side tilted this way as well? It would still, and then the lines matched up. If I move this over and I move this over, what shape is that now? It's a parallelogram. With the same exact sides, it turned into a parallelogram. And so that's why that structure is not being supported properly. Whereas when we have a triangular support, now it has rigid, it's triangle rigidity, and the properties keep it held together. Okay? So, I have a simple video, and I don't know if it's going to show very well. It's just a very simple video. And so a person constructed 2 things, and yeah, it's not projecting well at all, but I'll give you the basics and I'll show you a little bit. So they made a rectangular support structure, and this is a weight, and this is a triangular structure, and this is holding up a weight. And then it's kind of locked in by some Lego supports over here in each corner. So they're both built the same except for the shape. And then what the person's going to do is it's going to shake it. And watch what happens. And it's in slow motion so you can see it. Watch what's happening to the structures as the shaking is happening. Look at how much this is bending back and forth. It's swaying back and forth versus this, which there's no bend at all. And the person starts shaking it more and more, and it becomes more dramatic. But you can clearly see the strength of the triangular structure versus the rectangular structure. So the video goes on and on like this. Doesn't stop, but I think you get the point. So triangles play an incredibly important role in engineering and architecture and building structures all over. Okay? Does that mean everything's built out of a triangle? No, because we also have very strong elements that we can use to build things, like the desk you're sitting at. It's not made out of triangles, and it's still supported because it's made out of metal and sturdy wood. But if we applied enough force to it, it would bend and change shape. Whereas if it had been made out of triangles, it wouldn't be able to. Okay? So the point is this. It's a simple question to answer. Explain why the bench with diagonal supports is stable. Because triangles can only have one possible shape based on its size, whereas quadrilaterals and other shapes can have different shapes. Okay? Anyone have any questions about that? Okay, no questions? Your homework, page 234. You're doing numbers 5 through 20. And you're doing number 26, which will be 4 points. And that is a total of 20 points. And you're going to do the at-home tutor for lesson 4.5, or read the pages of the next section. And you're going to have a quiz on Wednesday. That will be for lessons 4.1 to 4.4. So it's not my preferred way of doing things, but if I don't do it, well, it's never going to get done. So you have a day off tomorrow, so you have time to do your work, study, prepare yourself. You will have to know the postulates and theorems up to this point. Okay, I did not get to give back your tests from last chapter because so many people missed it or whatever, blah, blah, blah. Here you go. Or did I give it to you and then I said you had to give it back? Okay, so you already said it. Here you go, now you can keep it. Oh, what did I give you?
I don't know because it's weird because I'm like, are you forcing it like